When a precision drone or a critical medical device engages its motors, you expect the power supply to hold steady. But often, the moment the heavy load is applied, a fresh 12-volt battery drops to 10.4 volts. We are often taught to treat a power source as a fixed variable. In introductory physics, a 12-volt battery is frequently represented as a source of constant potential, defined entirely by its label. In practice, a battery sitting disconnected on a desk, its open circuit state, produces one measurement. Connect it to a heavy load, and the measured voltage immediately decreases. Energy must be conserved, which means we have to account for where that missing potential goes when the circuit is active. To find the answer, we have to look past the external casing and examine the physical chemistry inside the cell. The voltage printed on a label represents a theoretical maximum rather than a guaranteed delivery rate.
To understand the difference, we first have to define electromotive force, or EMF. A standard electrolytic cell consists of two electrodes, a positive plate, P, and a negative plate, N, submerged in a chemical solution called an electrolyte. Within the solution, these electrodes exchange charges with the electrolyte. The positive electrode develops a positive potential, V+, relative to the liquid at point A. Similarly, the negative electrode develops a negative potential relative to point B. When no current is flowing, the electrolyte maintains a uniform potential. The total potential difference between the two electrodes is the sum of these individual potentials. We define this total as epsilon, the electromotive force. Electromotive force is a historical term from a time when the phenomenon was not fully understood. It is not a force measured in newtons, but a potential difference measured in volts. In this static state, chemical reactions reach an equilibrium. The separated charges are held in a state of high potential energy, available to perform work once a path is provided. EMF describes the cell's internal chemical pressure at rest. However, this is only the starting point for a working circuit. The dynamics of the system change the moment a switch closes the circuit through an external resistor, such as a light bulb. A steady current begins to flow from the positive terminal to the negative through the external wire. To complete the loop, that current must then flow from the negative terminal back to the positive terminal through the electrolyte. The electrolyte is not a perfect conductor. It possesses a finite resistance that the current must overcome as it moves through the cell. This is internal resistance, denoted by a lowercase r. It is an inherent physical property of the materials inside the battery. Just as an external component generates heat, moving charges through this internal resistance requires energy. This energy is dissipated within the cell itself. Internal resistance explains why the voltage available to the external circuit is always lower than the theoretical maximum once the current starts moving. The voltage actually measured between the terminals P and N during operation is called the terminal potential difference, represented by a capital V.
We can map the potential throughout the cell. There is a jump at the electrodes, but as the current moves through the electrolyte from point B to A, we see a potential decrease. We calculate this internal ohmic loss by multiplying the current, I, by the internal resistance, R. This allows us to define the terminal voltage as the EMF minus the product of current and internal resistance. The negative sign is necessary because the current inside the electrolyte flows from B to A, which is the direction that opposes the potential. Simultaneously, the external circuit obeys Ohm's law. The terminal voltage V must also equal the current I multiplied by the external resistance, capital R. This makes terminal voltage a variable. If you increase the current or use a battery with high internal resistance, the voltage drop increases, pulling the available potential further below the EMF. While EMF is a fixed property of the cell's chemistry, terminal voltage is a measure of the cell's performance under a specific load. Since both equations solve for the terminal voltage, V, we can combine them. The external drop, IR, must be equal to the total supply, epsilon, minus the internal drop, IR. By solving for current, we get a single formula for the entire circuit. Current equals the total EMF divided by the sum of the external and internal resistances. This shows that the current is limited not just by the device being powered, but also by the physical resistance within the battery itself. If the external resistance R is infinite, meaning an open circuit, the current becomes zero. In this specific case, the terminal voltage equals the EMF. If we short-circuit the battery by making the external resistance 0, we reach the maximum possible current. In this state, the current is limited only by the internal resistance, R. This state is dangerous because all energy dissipation happens as internal heating. This can lead to thermal runaway, a condition where increasing temperature triggers further chemical reactions, causing the battery to overheat and fail. This equation provides a complete description of the circuit loop. It accounts for both the chemical energy supplied by the source and the physical resistance encountered along the entire path. Internal resistance varies by design. Dry cells usually have much higher internal resistance than electrolytic cells, like the lead-acid batteries used in vehicles. Low internal resistance is critical for high-drain applications. Devices like electric vehicle motors or camera flashes require a large surge of current that would cause the voltage of a high-resistance battery to collapse. We have moved from viewing a battery as a simple static potential to seeing it as a dynamic system limited by its own internal makeup. Internal resistance is the physical link between theoretical physics and the practical engineering of electrical devices. The next time you look at a power source, do not see a constant reservoir. See a system defined by the relationship between chemical supply and internal resistance. Understanding these relationships is essential for managing the energy demands of modern technology.